we were talking about 15.4, the tangent plane, tangent planes, and linear approximations. Okay, and just to remind us where we were looking at a function, right, which went from R2 to R, right? And so it's a function whose graph, gives you some sort of surface, right? Gives us some sort of surface in R3, right? And we were talking about a tangent plane to the graph of f at x0, y0, z0, where z0 is f of x0, y0, right? So there's some point x0, y0 here, right? And then on the graph, right, there's the point x0, y0, z0, where z0 is, of course, the height, right? The height is the value of f at that point. This is your z. And what we said was that if your graph is differentiable, then you take the you can figure out the equation for the tangent plane, right? We saw that the equation for the tangent plane turned out to be z minus z0 is the partial with respect to x, and x minus x0, plus the partial with respect to y, times y minus y. Right? And this was the equation for the tangent plane, and we remember this z0 is again f of x and y0, right? So if we move this to the other side, right, we see that the equation for the tangent plane you can write like this: f of x, x0, y0, x minus x0, plus fy, x0, y0, y minus y0, plus z0. So this describes the z. This describes the z height, and so we said let's call this thing the linearization. Right? Let's call this thing the linearization function. Right? The linearization function. So this is the function whose graph is the tangent plane. So we let L of xy be this thing here. And I'm going to write it like this: f sub x, x naught, y naught, f sub y, x naught, y naught, times the vector x minus x naught, y minus y naught, plus f of x naught. Okay, this thing on the right is the same thing as this thing. So what I'm using here is matrix notation. How many of you are not familiar with matrices? Okay, that's fine. So let me do it just like a quick and dirty introduction to matrices and matrix multiplication. So a matrix is just an array of numbers. Who am I talking to? Who raised their hands? Okay, great. So a matrix is just some sort of n by n array of numbers. Right? It's some array of numbers with a size, and usually one writes an m by n to mean that it has m rows and n columns. Okay, so if I draw something like this, 1, 2, 3, 4. This is a 2 by 2, right? A 2 by 2 matrix, right? This is a 2 by 3 matrix, right? 2 rows, 3 columns. Okay. Okay. So now there's something called matrix multiplication. So So maybe I should tell you what addition is before I tell you what multiplication is. But in some sense, you guys don't need it. So just as an aside, if you have two matrices the same size, and you want to add them together, then that's just done component-wise. So you create a matrix, again, of the same size, 1, 2, 3, 5. So you just add it entry-wise. Okay, so matrix addition is done entry-wise, and only with matrices of the same size. You can't add matrices that are of different sizes. We don't allow it. Okay, but we're not going to need matrix addition anyway. What's going to be useful for us is matrix multiplication. You've all seen the dot product. Okay, so matrix multiplication goes like this. You have two matrices, A and B. So you have two matrices, and one is an m by n matrix, and the next one is an n by r matrix. n by p matrix. And in that case, you're allowed to multiply the m by n by the n by p guy. Okay, that's the only time you're allowed to multiply matrices, when the guy on the left has the same number of columns as the guy on the right has rows. Okay, the number of columns of the left guy must equal the number of rows of the right guy. Okay, and what you get a m by p matrix. You get an m by p matrix, and it's made in the following way, where the ijth entry of AB is the dot product of A's ith row against B's jth column. Okay, and that's why you need the number of columns of A to be the same as the number of rows of B, because otherwise you can't take the dot products of the rows of A against the columns of B. Right. Let me draw a picture. Let me give an example. So let's say that we'll take a 2 by 3 and a 3 by 2. Okay. So take a 2 by 3 matrix, 1, 2, 3, 4, 5, 6. That's matrix A. And we take a 3 by 2. Right. 0, 0, 1, 0, 1, 5. Okay. So the rule is going to be that, right, so here's A, and here's B. And so you see what you're going to get. You're going to end up with a 2 by 2. Okay. Right, so remember, m by n, n by p results in an m by p matrix. Okay. And so, we're going to end up with a 2 by 2, where this entry is going to be the dot product. This is the first row, first column. So we're going to take the first row of this guy and dot it against the first column of this guy. Okay. So what do you get? You get 5. Right. This is the first row, second column. So we take the first row against the second column. We get 15. Here we get the second row, second row, first column. We get the second row against the first column. Second row, second column. Second row against the second column. Take dot products. You guys see that? You guys who haven't seen this sort of thing before. So matrix flow, is that okay? Matrix multiplication. What happens if you do it the other way? What if you multiply B by A? 0, 0, 1, 0, 1, 5, 1, 2, 3, 4, 5, 6. Well, what's the size? First off, what's the size of the result? We get 3 by 3, right? Okay. And what will the entries be? Maybe those of you who haven't done it before, try and fill in the first column. Say, do the first column. Yeah, do the first column. You can do it in your head if you like. So what is it? No, you haven't done it. You see, now if you're not writing, I can't tell if you started or you finished. What's the first one?
5. 0.
0, right? Because you're gonna take the first row against the first and dot it against the first column. Right? So you get 0 times 1 plus 0 plus 1. Okay. What's this one?
Is it 9?
No.
Is it 3?
Yes, it is 3. Right? Because it's the second row, the third column. So you're going to take the second row of this and dot it against the third column here. So you put 3. Okay. Alana, what's the middle one?
2.
2. Okay, so basically matrix multiplication is just a lot of dot products. Okay, so you say, okay, I'm going to take the dot product of these guys, and then I take this row against the first column, I get 0 against the second column, I get 0 against the third column, I get 0. This row against the first column, I get 1. Against the second column, I get 1. The third column, I get 1. This one against the first I get 21. I get 27 and 33. Right. Okay. So that's matrix multiplication. Okay. Everyone is starting to get a sense of matrix multiplication, what it does. So what's going to be important for us is this: that if you have a matrix, suppose you have a matrix that's an m by n matrix, then so A is an n by n matrix. If I hit it with an n by 1 vector, n by 1 matrix, but you can think of a vector as sort of like a matrix. Okay. Right? It's an n by 1, right? So I have got an n by n guy here, n by n guy here, and I've got an n by 1 guy here. Well, I'm going to end up with a what? Well, it's going to be m by 1, right? AB is going to be an m by 1 guy, right? Right, like if I have, right, 1, 2, 3, 4, 5, 6 again. Right. And I have x, y, z. I have some vector x, y, z. Okay. And I hit it. Well, I'm going to get, this is 2 by 3, this is 3 by 1. I'm going to end up with a 2 by 1. Right? I'm going to end up with a 2 by 1 die. And that's going to be x plus 2y plus c, 4x plus 5y plus 6c. Right? I'm going to end up with something. I'm going to take my 3 vector, my vector in R3, and I'm going to get something out of it, which is a vector in R2. Right? Everybody see that? Okay. And this is going to be the important thing, that if you have a matrix that's n by n, you can think of it, any n by n matrix gives a map from Rn into Rm. Right? Here's a matrix. Lo and behold, it takes in, you can think by left multiplication, you can see that it takes something in R3 and turns it into something in R2. Okay, so any matrix corresponds to a map from one vector space to another vector space. Okay. Really okay? Melissa?
Yeah.
You don't. Yes. So it gives you a map from here to here. And if you think about that, if I have a number 5, it's a number 5, right? But also I can think of it as a map from R1 to R1, right? Namely, it's the guy that takes things and multiplies them by 5. Okay, right? This is the same thing. Any matrix also, right? This 5, you didn't realize it when you were a kid, but it's actually a 1-by-1 matrix. Right? This is a 1-by-1 matrix here, right? And as such, it gives you a map from R1 to R1. Okay. This guy is a 2-by-3 matrix. It gives you a map from R3 into R2. Okay, so now that, okay, so what I hope that you all who haven't seen matrices before have gotten out of this is just 2 things. One, you can multiply by matrices, and hopefully you have some sense of how that happens. 2, and this is the thing that I hope everybody gets, a matrix determines a map. A matrix determines a map from one vector space into another vector space. Okay, so now we're back here, and I've rewritten like the linearization is this thing here, but I'm going to rewrite it like this using matrix multiplication notation. This is your matrix. This is another matrix. It's a 2-by-1 and a 1 against a 1-by-2. I'm sorry. This is a 1-by-2. Excuse me. 1-by-2 against a 2-by-1, right? And as such, it'll give me a 1-by-1, namely a number. Okay, what number does it give me? It gives me f sub x, x naught, y naught, times x minus x naught, plus, right, it gives me the dot product of this thing against that thing, right? Which is this thing up here. Right? Remember how matrix multiplication works, right? You've got 1-by-2, that's a 2-by-1. That's going to give you a 1-by-1, where the entry is the dot product of the first row against the first column, right? So that'll give me a 1-by-1 whose entry is this times x minus x naught plus this times y minus y naught. A 1-by-1 matrix, which you can just think of as a number.
Then why do we express it as a matrix rather than just a dot product?
Why do we express it as a matrix? This is really to tie back into this is basically to make an analogy. To make an analogy with the one-dimensional case. Remember the one-dimensional case, the tangent line. What's the tangent line? It's f prime. The tangent line at C is f prime C x minus C plus f at C. Okay. So this is maybe you see how this is now entirely analogous, right? It's entirely analogous, right? You say what we have here. This thing corresponds to f prime C, right? This thing corresponds to this thing ought to be the derivative of your function, and in fact that's how we're going to define it. Okay, this thing here is the difference between x and between xy and x on y naught. Right? Right. And this thing here is the value of f at that point. Okay? Okay. And yeah, and so what happens is, I'm sort of jumping the gun, I'm really jumping the gun here, but what happens for functions from Rn into Rm, from functions from Rn into Rm, is that here you're going to have an m by n matrix. Here you're going to have an m by n matrix, right? And right, you'll take the Rn guy into Rm, right? And the matrix will consist of lots of partials. I'm not sure if we'll talk about it, but really that's what's going to happen. The derivative will, if it exists, will end up being a matrix of partials. So the derivative. So f going from Rn to Rm, f prime, if it exists, will be a matrix, an m by n matrix of f's partials. And this actually is not included in your book at all. This thing, what the derivative is, right? But it is the matrix that gives you the linearization of your function. It's the matrix that gives you a linear approximation of your function. This matrix is the one that gives a linear approximation of f near the point. Yeah, so I'm afraid we're not gonna go into that in any detail, but I hope you can think by analogy. Okay, right. In this case, right, we're going from R2 to R1. The derivative turns out to be this matrix that describes the tangent plane. The derivative turns out to be a matrix that describes the tangent plane. In other words, the matrix that gives you a planar approximation of your function. Okay. And in higher dimensions, it will turn out to be a matrix that gives you some sort of hyperplanar approximation of your function. We don't like to say hyperplane, and so we just say linear approximation. But it's not a line, it's a high-dimensional line. Okay. In any case, this is the linear approximation of your function, right? This thing is called linearization. And my kids make fun of me because I say okay too much. Okay. And my kids are saying, okay. So, yeah, that would be almost a sure square on the bingo game. You guys have seen the bingo game on my drawing? Yeah. I told you about the bingo game. Like again, I guess I didn't say it at that time. It would be now. Sure. Okay. Let's do some examples. Okay. So f of x, say, is x squared y cubed, and I'd like to know the tangent plane. What's the tangent plane at 1, 1, 1? What's the tangent plane at 1, 1, 1? Well, here's what we have to do, right? All we need to do is figure out the equation of the tangent plane, and that entails what does that involve? Just taking partials, right? So let's take partials. F sub x, xy, right? Take the partial with respect to x, you get 2xy cubed. F sub y, the partial with respect to y, 3x squared y cubed, y squared. Right? we evaluate those things, fx at, so where do we evaluate this?
1, 1.
At
the
1, 1.
first two.
Yeah, the first two, right? Because this is your x naught, y naught, right? The z is your, of course, f of 1, 1. Right? Okay. So f of x at 1, 1, well, that's going to be 2. F sub y at 1, 1 is going to be 3. Right? And so you write down the equation, right? It's going to be z minus 1 equals 2 x minus 1 plus 3 y minus 1. Okay, so this is the tangent plane. And what's the linearization? If I asked you to write down the linearization, what would you need to do? What would you do?
Don't you just add the 1?
Just move the one to the other side. Right? So you get this thing plus 1. Right? And if you wanted to, write this in a more suggestive manner, you could write it like this. You could write it like this. Right? This is in reality what's really going on here. Okay. So, for example, if I ask you, tell me what is 1.01 squared times 0.99 cubed? What is 1.01 squared times 0.99 cubed? Okay. And I don't want you to square 1. I don't want you to tell me exactly what it is, but I'd like you to use the linearization to give me an approximate answer. So here's the question. Use the linearization. Use L of xy to approximate this thing. Right, so what's the answer?
2 times 0.01 plus 3 times negative 0.01 plus 1?
Mm-hmm. Right, so you've got 2.01s, you've got minus 3.01s, so you've got minus 1.01s. So 1 minus 0.01, namely 0.99.
Can you write that down, please?
Yes. So you say, well, L of 1, right? L of 1.01.99 is going to be, this is a linear approximation at that point, what's going to be 2 times 1.01 minus 1 plus 3 times 0.99 minus 1 plus 1. Right? So that's 2 minus 3 of those guys plus 1, namely 0.99. And that, if you actually calculate it, the true answer, so f of 1.01, 0.99, in fact, turns out to be 0.98980201. So you see, it's actually, the linear approximation is pretty good. And what we're doing here, is this okay? Everyone? Well, so what we're doing here is, of course, exactly analogous to, taking the value, to taking the tangent plane, taking the tangent line to some function around C, and then somebody says, what's the value here? And you say, well, I don't know, but it's easy to calculate the value of the line there, right? You take a linear approximation. This is the linear approximation. You notice that there's no squaring, there's no cubing. It's all linear terms. It's all linear. This is the linear approximation, right? It's something that an elementary school student could use, right? And say, okay, well, I don't know. I'm an elementary school student. I don't know what you mean by squaring and cubing, but I have this linear approximation and I can calculate it. Okay. Just like if you're approximating square roots, right? It's handy to take the linearization and then make a guess as to what the square root is. Do you guys know the Babylonian algorithm? Have you seen the Babylonian algorithm? Maybe if there's time, I'll talk about it. That's sort of that's equivalent to linearization. I've sort of forgotten how to do it, but hopefully by the end of class I'll remember. Okay, yeah, more important, let's go on with the examples. Okay, so number 2, say, f of xy is, say, 1 if x is 0 or y is 0. And it's 0 if xy is not 0. Okay. So here's the function. What does it look like? It takes the value 1 above the axes. Right? Whenever x is 0, it takes the value 1. Whenever y is 0, it takes the value 1. And everywhere else, it's 0. Everywhere else, it's 0. Suppose I ask you, find the linearization of f. So I ask you to find the linearization of f. Well, what would you do? What would you need to do? You need to take, again, partial derivatives, right? So you say, okay, well, I'm going to take the partial with respect to x. Find the linearization of f at 0, 0. Okay, so you take the partial with respect to x at 0, 0. What's the partial with respect to x of this function at 0, 0? 0, right? You remember you'd slice through and you'd see that you get a constant function. Constant function has a derivative of 0. Oh, your shoes are magnificent. And then partial with respect to y, 0 again, right? Because again you slice and you see, oh, my function looks like it's a constant, right? So I get zeros. Right, so my tangent plane is going to look like z minus 1 is 0 plus 0. Right? In other words, my tangent plane is just a constant plane at height z equals 1. Right? And so my linearization also would be just a constant. You see that if I wanted to approximate, if I said, what's the value at 0.1, at some other, no matter what value I take, I'm going to get 1, right? And you see that that's not so good, right? That's not so good. It's not a good approximation to my function, right? Because my function is very discontinuous, right? My function is very discontinuous. It's not really the sort of function that is well approximated. So, right, this guy is really not well approximated by a plane. Right. In fact, it's very discontinuous. And so this sort of shows you one thing about the partials that's a little bit that, even if the partials exist at a point, the function could be discontinuous there. So notice, even though fx, fy exists at 0, 0, f is discontinuous there. Right? that's very different from the one-dimensional case. Right? In the one-dimensional case, as long as your derivative exists, then you're continuous there, right? You know, you've seen this thing, right? This the continuity, right? If the derivative f prime c exists, then f is continuous. F is continuous at c, right? But here, all the partials exist, but the function is discontinuous there, right? So that's very different. You know, a difference from the one to the two-dimensional case. And further, you know, if the derivative exists in the one-dimensional case, then the line approximates it, right? But here, both partials exist, but the plane doesn't approximate it well. Okay, so this sort of leads you to understand that the partials are not a good replacement for the notion of differentiability. Okay, the partials are not. You know, the partials all existing there is not what we want to call differentiable. Okay. Instead, we have a different definition of differentiability. So here's what the book gives. I don't quite like it, but it's not that bad. So, so you have some function from R2 to R, and you let L sub f be the linearization of f near a point x naught y naught. We say f is differentiable at x naught y naught if f of xy equals LF equals its linearization plus some function of the difference between x and x naught and some function of the difference between y and y naught, where these functions e1 and e2 functions go to 0 as xy goes to x naught. So let me give you, intuitively what this is saying. Right? What is it saying? A function is differentiable at a point if, oops, this should be x comma y, not x minus y, sorry. A function is differentiable at a point if the function is well approximated by its linearization. Right? That's basically what it's saying in English. Right? The function is its linearization plus some things that vanish as xy goes to x naught y naught. Right? So this is really saying if f is basically its linearization. Right. F is its linearization plus some things that vanish as xy goes to x naught y naught. Okay. That's what this is. That's what this is. So I don't like this. Let me give you the proper definition in a second. You notice that one thing that's very unsatisfying about this is that it doesn't say what the derivative is. What's the derivative of f? It doesn't tell you. Right? There is no derivative of f. Okay. Let me give you another definition, which is more proper, but a little more. Let me give you the real definition. That definition is fine, but let me give you another one, which is actually how you do it. So we say f from Rn into R1 is differentiable at x naught if there exists a linear map A going from Rn into R1. Okay. And really what we mean by this is a matrix, okay, that is a 1 by n matrix. Such that the limit of f of x naught plus h minus f of x minus ah over the absolute value of h is 0 as h goes to 0. In which case, we say the derivative of f at x naught is that matrix A. In fact, it turns out that if f is differentiable at x naught, then that matrix turns out to be the matrix of partials, f x1 first partial evaluated at x naught, second partial evaluated at x naught, the nth partial evaluated at x naught. Remember, when I write this, I mean f sub 1 or f sub x1. Right, the partial with respect to the first variable evaluated at x naught, partial with respect to the second evaluated at x naught, etc. So, but this is actually the same. This is actually sort of the same statement. Okay, I'll hold up this. There's a copy. Okay, so if you look at this thing, you might think, oh, is this the same thing as that? This is actually, if you look at it, right? This is saying that your function is basically a linearization. This thing here is the linearization, okay? And this is your function. So it's saying that your function minus the linearization, even when divided by this thing, goes to 0. In other words, your function is well approximated by the linearization. You can if you translate this also says, right? F is basically, right? This says that f of x naught plus h is basically the linearization plus the value at x. This should be x naught. your function nearby x naught is basically this linearization, right? This is exactly the same thing that we said before, right? F of c plus h is f prime c times h plus f at c. Right? F at x is f prime c x minus c plus f at c. Right? These are the one-dimensional analogs, and this is the higher dimensional analog. Right? A is f prime x naught. So I hope you guys are seeing the analogy. We're not gonna really get into this, but this is the analogy. So let me just say one thing. Let me just give you one thing that will be useful. Right. See, your question should be, well, when do we know a function is differentiable? Right? When do we know a function is well approximated by its tangent plane? And we have a fact. Right? When do we know that it is differentiable? In other words, well approximated by its linearization. Okay, we have a fact. Here it is. If fx and f sub y exist and are continuous around x naught, y naught, then f is differentiable at x naught, y naught. So as long as this happens, then it's okay to use your linear approximation. This will allow you to avoid situations like the bad function we had before. Right? It'll say, oh, it will tell you that it's not differentiable. At least, well, yeah, it will tell you. It won't tell you that it is differentiable. Okay, that's it for today. I actually.